Hello everyone, my name is Lorenz and welcome to this presentation on improved gravitational radiation timescales. So as you all know, Elisa will measure gravitational waves, and these gravitational waves mostly come from pairs of compact objects such as black holes, supermassive black holes, or pairs of a large supermassive black hole and a stellar mass black hole. And a very useful thing to know about these pairs of compact objects is how fast from a particular initial condition they will spiral in and eventually merge together. So let me set the scene. We have 2-point masses and we want to describe precisely how quickly they will merge together from an initial condition that comprises in a particular semi-major axis, which in this amazing little drawing you can see it's this line here, and eccentricity. So the eccentricity basically tells you how squashed the orbit is. And to answer the question of how fast they merge, we start as usual from Einstein. In 1916, he found out that a mass quadrupole in general relativity will emit energy and in gravitational radiations, more specifically energy and angular momentum. And in 1963, Peters and Matthews, these are names that you will hear often in this presentation, realized that a binary made of 2-point masses has a quadrupole. And this amazing little drawing, you can see I divided the binary in 4 quadrants, and 2 of them have mass and 2 of them don't have mass, so it's a quadrupole. And in 1963, Peters and Matthews answered, okay, what are the effects of this energy and angular momentum flux on the binary? So what did they do? Well, they said, I mean, Newton told us that the semi-major axis of a binary is essentially the inverse of its energy, right? You can see this formula here. And the eccentricity of a binary is some sort of combination of the angular momentum, in this case specific angular momentum, and the energy. And so they said, I mean, if energy and angular momentum change in time, also their semi-major axis and eccentricity will change in time. And they found these very famous evolution equations for the semi-major axis and the eccentricity. Why are they useful, especially this first one? Well, this equation, dA dt, tells you that in a finite amount of time, your binary will shrink and shrink and shrink and shrink and eventually merge. And with a few tricks and approximations, this is not the only thing that they did, but one of the things that they did in this amazing paper in '63 is to find an estimate for this amount of time that it takes for a binary to eventually merge from a particular set of initial conditions. And this timescale is called Peters timescale and is used right now in a varied range of applications, and most of them have to do with the upcoming LISA experiment. So why is it useful to have a quick and easy estimate of the decay time that is an analytical formula? Well, first of all, it's quick and easy because it's an analytical formula, but more precisely, it's very useful if you're interested in very large simulations. For example, imagine you're following 10 million binaries that are forming, and eventually they will go underneath your minimum resolution. And you're interested in knowing, okay, from the moment they go below resolution, how much time does it take for them to merge? Instead of solving these 2 equations 10 million times, you just plug in semi-major axis and eccentricity 10 million times, and that's of course much faster, and then you get the result out. Also, it's used extremely often to estimate the efficiency of this GW, gravitational wave induced decay of the binary versus other dynamical processes, for example, 3-body interactions or dynamical relaxation. And on the right here, you see a very typical plot where this timescale of gravitational wave induced decay from now on GW timescale is equated with other important timescales, and then some lines are drawn in phase space. And remember, these type of plots, it's always with semi-major axis on the left and 1 minus eccentricity below. So you hear these lines, to compute them, you just take Peter's timescale and equate it with another timescale. Okay, but of course, this is just an approximation, right? This Peter's timescale, and it has some limitations. First of all, the equations that I showed you before cannot be solved exactly analytically. And Peter's solved this problem by basically saying, I don't care so much about the eccentricity evolution. I'm just going to put in the initial eccentricity. The argument is more sophisticated, but I will skip over it for now. And this alone, for very eccentric orbits, can bring about an error of a factor 8. And most of LISA sources will probably have moderate to high eccentricities, especially EMRIs that can have extreme eccentricities. Second of all, people that know post-Newtonian theory will know that Peter's timescale and in general those evolutions equations are just the lowest order in post-Newtonian expansion. Post-Newtonian expansion is an approximation of GR, and this is the lowest order. It's the 0th order. And so one expects that for highly relativistic orbits, this Peter's timescale will start to fail at some point. So how does one go about improving this Peter's timescale that we have seen is still very useful? Well, you have to fix this eccentricity problem, and also you have to include higher orders of the post-Newtonian theory. And how do you do that? Well, you have to add higher order multiple radiation, but also you have to update the parametrization, because this formula that the semi-major axis is 1 over the energy, it's not true in GR, it's just an approximation. And so you have to add the next leading orders to it. Here I show basically some examples. Let's focus for a moment on the left plot. So this is an evolution of a binary that starts at a particular semi-major axis with a moderately high eccentricities. The black line is evolved using Peter's evolutions equations, and the other colors are adding post-Newtonian orders. And you can see already here that even the Newtonian numerical solution is 4 times larger than what Peter's formula tells us. And here, because here it's denoted by 1, this is time normalized with Peter's formula. And if I add post-Newtonian orders, the real time, or the more precise timescale of decay, is even further, is even larger. And you can pause the video and look at the other plots, but the takeaway message is that adding post-Newtonian orders kind of messes up. Some orders increase the timescale, some order decreases. But it's pretty obvious that Peter's formula, if one is interested in being precise about the timescale, is not sufficient anymore for LISA sources, because they are very eccentric and highly relativistic. So what we sought to do in our paper is to basically update Peter's formula, but in a way that it's still simple and can be used in the same way that Peter's formula has been used up to now. And what we did is find some ratios that can be multiplied to Peter's formula to essentially correct all of these problems. And for the derivation, of course, you can, for the detailed derivation, you can check out our paper on it. So this is Peter's formula, and this is a combination of factors that will correct for these errors. And something that we've been working on right now is to include the spin of the central black hole, especially in the case of EMRIs, because it seems that it will have a major impact on it. So these two plots are just to show how much Peter's timescales actually fails and how using our corrected formula can resolve these issues without complicating things too much. On the left plot, this is basically the result of numerical integration, spitting out the true decay timescale. And on the left, we have the decay timescale normalized with Peter's formula. On the bottom, we have 1 minus eccentricity. And you can see that for eccentric orbits and highly relativistic orbits, the error goes up and up and up to factor of 10 or even more if you take more relativistic sources. And these black crosses are the result using this corrected formula. So you can see that it basically gets rid of all the error. And on the right side, we have basically the same plot, but normalized. We factor out the effect of eccentricity. So this is purely the effect of the post-Newtonian corrections. And you can see that only the post-Newtonian corrections already can mess up your timescale by 30, 50, 60%, even 100%. And this might be relevant or not relevant depending on the application. And our fit essentially gets rid of all of this error. Okay, so what are the consequences of an updated Peters formula? For a moment, let's remind ourselves of this type of plot where we equate Peters timescale with different other important timescales and separate phase space into different regions. Well, let me fix this for a second. As a first example, let's equate Peters timescale and our corrected version with a fixed time. For example, in this left plot, we equate it with 10 to the 4 years, 10 to the 3 years, 10 to the 2 years, etc. What does it mean? It means that sources that lie on these lines will take 10 to the 4, 10 to the 3, etc. years to decay from that point. And we can see here the old result with Peters' formula is denoted by these dashed lines, and the corrected results are denoted by the solid lines. So what happens here? Well, it's pretty clear that for a large range of phase space, not correcting Peters' formula can make you confuse sources that decay in, for example, 100 years with sources that decay with 10 years. So it's a factor of 10 difference for quite a lot of phase space. And this might, for example, bias your selection of interesting sources or not. On the right-hand side, we see a very similar plot, but this time it's not a fixed time scale, but it's equated with the time scale of dynamical relaxation inside the nucleus of a galaxy. So these different colors denote different steepness profiles for the central region of a galaxy. And here the dashed lines are computed with the old Peters formula and the solid lines with the corrected versions. So things that are below these lines are interesting EMRI candidates, extreme mass ratio in spiral candidates. And you can see that correcting Peters' formula shifts these lines down and basically slices off large regions of phase space. And so we expect that the actual number of interesting EMRI sources will be decreased by probably a lot, because if you slice away this slice of phase space, what you're actually doing, you have to cube the volume, because this is semi-major axis, and the amount of phase space that you're taking away is the width of this slice cubed. So we think that this correction to Peters' timescale will have a significant effect on, for example, rates for EMRIs. And these are just two examples, but the takeaway message of the whole presentation is that it's time that Peter's timescale gets an update. Why? Because Lisa sources are very eccentric and highly relativistic. And so I hope that this presentation was interesting, and I hope that you can use it to do some more precise estimates of this timescale. And I just have some recommended readings if you're interested in this stuff. For example, of course, our paper, we not only calculate this correction, but we also briefly discuss all the ingredients that we need. And of course, I recommend the original paper by Peter and Matthews. This is amazing. It's super elegant and clean, not like post-Newtonian theory. And if you're interested in post-Newtonian theory, then I can recommend some very complete and detailed reviews of post-Newtonian theory, namely von Schäfer 2010 and Blanchet 2006. Very different approaches, but both very worthwhile. So thank you for your attention, and goodbye.